Alrighty, so we're going to start 1.9 part 2 on inverse functions. So we covered a lot of ground in part 1 about this relationship, the opposite operation that undoes this F inverse. So today we're going to focus on the algebraic approaches to finding inverses. So yesterday we looked at numerical and graphical primarily. So looking at tables of values, how do you find the inverse? You switch the x and the y. Looking at a graph, how do you find the inverse? Well, you reflect over the line y equals x. Remember, it has that symmetry. But also you can look at the ordered pairs on the graph and just switch the domain and the range. And we talked about how you verify that two things are inverses. You do that composition, f of g, g of f, and see that you get the identity function x. So today we're going to focus in on the algebraic approaches, like working with the equations themselves. How do you know that something's an inverse? So to start off as a warm-up, I'd like you to pause the video, look back from yesterday, and I'm going to have you look for these two definitions. Horizontal line test, so we haven't talked about that yet in my little brief summary from part 1. So what is the horizontal line test and what does it tell you? And then what is an inverse function? How would you describe it in your own words? And then we'll talk about those. All right, so let's see how this compares with what you wrote down. So F inverse, the notation we use, that F with a little -1, which remember is not a reciprocal or an exponent, it just means inverse. So when you see F with that little -1, you say F inverse or the inverse of F. It's the function that undoes the original function, the opposite operation. So like multiply, divide, squaring, square root, they undo each other. The domain and range are interchanged or switched. Horizontal line test. If a horizontal line touches more than one point on a original function f, then its inverse is not a function. One of the examples we used yesterday was a parabola, remember? If we do a horizontal line test on a parabola, it intersects that parabola at two places. That means when you do the inverse relationship, so remember we have that relationship over y equals x, it's that reflection. When we look at that inverse relationship and we do the vertical line test, it's going to touch more than one point because remember we're switching the x's and the y's. So if there's two y's on the original, there's going to be two x's on the inverse, not a function. So horizontal line test is a great, quick, easy tool to be able to know something about your inverse. So we're going to be using that again today when we algebraically find inverses. All right, so let's talk about how you actually do that. They give you a lot more spots to fill in. I sort of condensed it down a little bit. So how do you find an inverse of a function f algebraically? That means using the rule or the equation. So you're using the horizontal line test, first of all, to think about if the inverse of that is going to be a function. So if you want to think about the graph of your original function, think about the horizontal line test, then you know something about the graph that you're looking for. Think about that symmetry. You can get a little bit of an idea of what that's going to look like, and we're going to tie that in today. But to physically, algebraically do that, we're looking at this number 2. You switch the x and the y. That's what inverse means. And then for user friendliness, we're going to solve for y. Even think about like using your graphing calculator. If you wanted to graph an inverse, you don't want it to be x equals, right? Because you can't even type that into your calculator. So the convenience sake is the solve for y. The actual finding of the inverse stops right here. That is the inverse. That's what it is. But this is for user friendly to make it something we can use. So we're going to combine the horizontal line test for our thinking along with this algebraic approach. So let's see if we can find the inverse of this function. And when they say if it exists, they means if it's a function. So we can always find the inverse relationship just by switching the x and the y. What we're also going to be checking for is the inverse itself a function. All right, so let's take a look at this equation. Y equals, or f of x equals 4x minus 5. Linear equation, so that's a line. What's the slope of that line? Slope looks like it's mx, so 4. Now, I think if you think back to part 1, we talked about do slanted lines have inverses that are functions? So think about how you would sketch this line, or you can graph it quick on your graphing calculator. What do you think about the horizontal line test? What would that tell you about the inverse? So I have mine up here in the calculator, -5, y-intercept, up 4 over 1, up 4 over 1. If I do a horizontal line test on this graph, it's only going to touch that line at one point. What does that tell me? Well, that means its inverse should also be a function. So by using the horizontal line test, the inverse should be a function. So that's going to tell me a little bit what about I'm looking for, and it has that relationship, that symmetry over the line y equals x. All right, so let's talk about algebraically. How do we find this relationship? For a lot of people, instead of saying f of x equals 4x minus 5, it's a lot easier to think y equals 4x minus 5. Replace out that function notation just for the switching of the variables. It makes it a little bit easier. So let's find the inverse. You switch the domain and the range. So I'm going to switch the x and the y. So I have just found the inverse. That is the inverse right there. So x equals 4y minus 5. Now the problem is with that inverse, it's not very user friendly. I can't put it in my calculator. So we are going to solve for y. Now, the harder your equation to solve for y, obviously the more work it's going to be. This one's not so bad. We just have to get the y variable by itself so we can use it a little bit easier. So first thing I would do would be add 5. So we get y, 4y equals x plus 5, then divide by 4. Algebraically speaking, we can talk about what way we like better. Some people might leave it like this, just as a fraction. Some people might actually divide that out, take everything in the numerator divided by 4, so 1/4 x plus 5/4. Both of those are fine. They're both the same equation. If you're thinking about slope-intercept form, the bottom one might be a little bit easier. And ultimately, to go back with notation, let's use the f inverse or the function notation. The inverse function then would be 1/4 x plus 5/4. Or you could write it, like we said, the x plus 5/4, also fine. So here's our inverse equation. Now my question for you is, what kind of equation is that? Well, it's linear, right? We have a degree 1. What's its slope? The slope of this one is 1/4. Remember how we talked about that relationship between slopes in part 1? If one's up 4/1, the other one should be up 1/4. Kind of makes sense, right? Domain and range switch, the y's and the x's. So go ahead and graph that one on your calculator too, and let's see if we can tell that symmetry relationship we talked about in part. And I'm even going to put the y equals x in there so you can really see that clearly. So we have the original function, we have its inverse equation, and then we have that symmetry that we can always see when we look at that y equals x line. The red equation, the one that we just did, yeah, if you pass a vertical line across that graph now, it's only going to touch one point. It's a slanted line. It's a function. Now remember, we knew that already because we did the horizontal line test on the original. So to find an inverse algebraically, we just find switch the x and the y, so the domain and the range, and then for user friendliness, we solve for y, and that process is always going to be the same. It was kind of the same as what we were doing even on our tables of values, right? We just switch the x and the y. All right, so let's try another one. So we're going to look at a fifth power, an odd power. It's very similar to a cubic, very similar to that, but it's to the fifth power. So we're going to take a peek and see, is the inverse of this a function? So we're going to think about what that might look like. So just so we can talk about horizontal line test here for a moment, you may not know what 1/3 x to the fifth looks like, so can you graph it on your calculator? All right, so it's a steeper version of x cubed. If you look at that, those odd powers, we know if we take a positive to an odd power, it's a positive answer, but a negative number raised to an odd power is always a negative answer. So we get that same kind of family of graphs as we had for x cubed. So think about horizontal line test now. If you pass a horizontal line across this graph, are you going to be able to, get something that inverse is going to be a function? Now, if you think about that, it kind of looks like every place you're only going to be crossing one. It seems like it gets super flat around the x-axis. So I want to make sure that they're not doubling up any values there, and it actually doesn't. If you zoom in right around there, so I'm going to adjust the I went just from -1 to 1. You can even tell it's still curving. It's always increasing. If you take the next bigger x value and you raise it to the fifth, it's going to be bigger than your last answer. It never actually goes completely horizontal in the middle. So for all of those outputs, there's only one. So by the horizontal line test, we can say that the inverse is going to be a function. So is the inverse a function? Yes, because it passes that horizontal line test. So we do know something about what the inverse is going to be. All right, so let's remember how we find this algebraically. So we're going to take this original equation, and again, sometimes it's easier to replace that with y. And we're going to just switch the domain and the range. So we're going to switch the x and the y. Now we have to solve for y. So this technically right here is the inverse. So we're done with finding the inverse equation. Technically, that's what it is. The solve for y is what makes it easier for us to put it back in our graphing calculator. So how would you solve this for y? I have a power and I have that multiply. So I need to get rid of the multiply first. How do you undo multiplying by a third? Well, you could divide by a third, but that gets kind of messy over here because people usually mess that up. So what's a different way? Well, instead of thinking of it as division, how about multiply by the reciprocal? So what if I times both sides by 3? That might be an easier way to deal with it. So that's going to give you 1. So y to the fifth, and then we have a 3 times x. What's the opposite of raising something to the fifth power? Well, it's the fifth root. So I'm going to take the fifth root on each side. So we get y equals the fifth root of 3 times x. Be very aware of where the radical is going to go. 3x is all on the inside of that. That's that argument on the inside, we call that. So we would switch up to our inverse notation here. F inverse of x is equal to the fifth root of 3x. Now, normally when we take roots, we're having this big conversation. Oh, we need plus or minus. You need plus or minus. Do you need plus or minus for a fifth root? In other words, if you multiply a number times itself 5 times, can that be either a positive or a negative answer to get the same value? So let's think about a fifth root of 32. And try that in your calculator. Fifth root of 32 is just 2, right? Because 2 times 2 times 2 times 2 times 2 times 2 is 32. But what's the fifth root of negative 32? Ooh, -2, different answer, right? So there's only one solution for this. There's only one possible outcome. So we don't have plus or minus like you would for an even root. So I only have one answer. And that's a key part to our conversation in this whole idea of the function being, or the inverse being a function. Because if I had more than one answer here, if it were plus or minus, then it's not a function, right? Because for every input, you've got to have exactly one output. So this graph should be something that's a function. So the opposite operation of a fifth power is a fifth root. Now we're going to graph that on our calculator. So I'm going to go in y2 and I'm going to type in this inverse. So hopefully you know where to find roots. You can go under your math, and it's number 5, like the x root, so you can do that one. That's a pretty quick way to get to it. You can also do the shortcut up above here. So this is the fifth root of, underneath our argument was 3x, and we'll take a peek at that graph. So just to show you that other place where fifth root is, if you do alpha window, it is under that menu as well. So whichever way you think is faster to get there. All right, let's go ahead and take a peek at the graph here. So, oops, I forgot to switch my, we'll switch my window back here. So here we go. So we have our original function, f, which is blue, and the inverse function, which is the red one. And so think about something that's very vertical. Its inverse is going across then. It's going to be very horizontal. If you think about a vertical line going across that red graph, it's only going to touch at one point. It's definitely going to be a function. And then I'm going to go ahead and put that y equals x in, just so we can see that relationship, that symmetry. Every function is going to have the symmetry with the line y equals x with its inverse, and that's definitely the case as well. So the horizontal line test told us a lot about what was going to happen, which is really helpful, but that solving for y allowed us to have the rule, the actual equation for the inverse algebraically. All right, let's take a look at another one. So we're practicing this algebraic approach. So we're going to find the inverse function of this. Oh my goodness. I want you to take a moment, pause the video, type this into your graphing calculator to see what the original function looks like. This doesn't look like any parent graph that we've talked about. It's kind of that rational function though, ratio, but kind of with a twist. So it's a little bit more complicated. So go ahead and type. All right, so when you take a peek at our equation and we graph it, it looks very much like that rational function. So when we talked about that ratio, or that the parent graph 1 over x having those asymptotes undefined places, let's think domain for a second. Do you see some asymptotes, some excluded values? It looks like there's a vertical asymptote and a horizontal. If you take a look at the vertical asymptote location, let's go back to our equation for a second. Think domain, we've got a fraction. What can't this bottom be? So if you set 3x plus 2 can't ever be equal to 0, and you solve this for x, you're going to get -2/3. And that's that location. If you look back at the graph, that's the place where that vertical asymptote is happening, right at -2/3. So that's that vertical asymptote. So when you think about the graph, it should fit with that. Now let's think about horizontal line test. If you pass a horizontal line up and down that graph, will you get something that is inverse that's a function? Will it only touch one point? And the answer is absolutely yes. You're only going to see that one location. So I'm going to take a look at that. So we have this vertical asymptote. This is at that x equals -3/2. And think about that horizontal line. There's a red one on there right there. It's only touching one point. But if I do a horizontal line down here, only touching one point. So this passes the horizontal line test, which means the inverse is also going to be a function. Now, the tricky part in this one is how do you find the inverse? Oh my goodness, this is a little more complicated. All right, so let's go ahead and see if we can find, the inverse equation. So again, I'm going to switch this out to y instead of f of x, just to make life a little bit easier. All right, so what you have to do is switch the domain and the range, the x and the y. So anything that was a y becomes an x, and anything and everything that was an x becomes a y. All right, so there's the inverse. If that's all I needed to do, gosh, then that'd be great. But if I ask you now, hey, I want you to type that into your graphing calculator so we can compare it to the original, that would be really tricky. So the solve for y part here is what makes this super interesting. So we want to solve for y. So remember, when you solve for something, you want to get any term that has that variable on one side and everything that doesn't have that variable on the other side. All right, so one of the things that makes this more complicated is you have more than one y, so that's tricky, but then there's also a fraction. So let's deal with the fraction right away. How do you undo dividing by something? Well, you multiply by it. So how about we multiply both sides by that denominator? We've always done that to get rid of a fraction. It makes life so much easier. So let's multiply both sides by that. Well, what happens over here is that divides to 1. Awesome. We've accomplished part of our goal in making this a little bit easier. On the other side, we just have 3y plus 2 times x. All right, so now if we want to solve for y, remember we want to get all the y's on one side, all the x terms on the other, I'm going to have to distribute this through. So 3yx plus 2x equals 5 minus y, to be able to get at all the terms separately. All right, so let's get all the terms that have y on one side. So I'm going to move those to the left. It doesn't make any difference, but we just have to choose. So I'm going to add the y to both sides. And I'm going to get everything that doesn't have a y to the left-hand side. So I'm going to subtract a 2x on each side. I'm just going to do this both at once so I can kind of take care of both of those things. So I have a 3yx plus the y that I'm going to add to that side. And then on the other side, I'm going to have a 5 minus 2x. Awesome. Okay, so now how do I solve for y? I've got two terms that have y in there. I got to get y by itself. Think of it this way. These both have y in it, so it's a GCF. So I can pull the y out. What would be left inside? Well, 3y plus, careful here, y times what would give you y? 1. Don't forget your placeholder. And now we're in great shape, because how do I undo what's happening to the y here? I have to undo multiplying by that 3y plus 1. I'm going to divide both sides by 3y plus 1. And when I do that, that divides to 1. We get y equals 5 minus 2x over 3y plus 1. So again, we can change over to that f inverse notation. So 5 minus 2x. Oh dear, why am I saying I miswrote here. This is supposed to be an x. I'm like, why do I still have y's? You're like, what's happening? 3x plus 1, pardon me, definitely an x there. So that's this term. Sorry about that. So that is an x. This is an x. So over 3x plus 1. So I have all my x terms on one side, the y term on the other. Sorry about that. That is definitely an x in that term. So careful on that. Make sure you make that adjustment. So my inverse equation is 5 minus 2x over 3x plus 1. So now I'd like you to go back to your graphing calculator. Let's see if we can type that in and see if we can see that symmetry. It's a little harder to tell on this one because they're very similar graphs, but they are reflecting over the line y equals x. So if you put in that y equals x, you are going to see that relationship. So they're very similar graphs. If you look at the equations, they are very similar as well. So the inverse of a rational function is another rational function. And if you look at just the red graph again, it would pass the horizontal line test, meaning or a vertical line test, meaning it is a function. So we knew that because of the horizontal line test from the original graph, from that blue one. So remember, we can always tell something about the inverse by looking at the original graph. All right, we're going to finish up with this one. The last one we're going to do is a cube root to start. So what I'd like you to do is go ahead, pause the video, graph this one on your calculator, and see if we can figure out something about what its inverse is. Think about the horizontal line test. Now, when you graph this one, so cube root of 10 plus x, I want you to take a peek at this. We're not really seeing the whole graph. Remember, cubing and cube root would be inverses of each other. So a cube, remember, is that vertical graph going up and down. It's one of our parent graphs. The inverse graph should be going across. If you think about what a plus 10 does to your graph, x plus 10 underneath there, that's going to be a shift of 10 units to the left. So the issue that I'm having with the graph, and I wanted to show you this so we could adjust and do what we need to do, is I'm not really seeing the whole thing. I'm going to adjust my window here, and I'm going to have this go to negative 20 for the x. I want to see more in that direction. Oh, there we go. We can see that inverse a little bit easier, so we can tell that, or that original function, that it's actually, we do have things below the x-axis as well. So that's the original. That's cube root. That's what a cube root looks like, and it's been shifted 10 units to the left. So now I want you to make a prediction. What do you think is going to happen on the inverse? So if my original function goes 10 to the left, which is negative in the x direction, what do you think the inverse graph is going to do? Remember, x and y switch. So it's going to be going in the y direction that same amount. So we're going to be having that negative in the y direction. So hopefully when you see that inverse and what's happening, you understand that undoing. So if it's in the x direction for the one, it's going to be in the y direction for the other. All right, let's talk about horizontal line test. What do you think? If you pass a horizontal line up and down this graph, are you only going to touch one point? Absolutely. So what do we know about the inverse? The inverse is going to be a function. So it passes the horizontal line test. So the inverse is a function. So when we look at the inverse, when we graph that, we're going to be able to tell it's a function. So let's see if we can find that inverse equation. So again, I'm going to start off with y equals. I think that's a little bit easier for people to work with. And then we're going to find the inverse by switching the domain and the range. So anywhere there's a y becomes an x, and anywhere there's an x becomes a y. So technically, there's your inverse equation right there. Now the problem is, again, not user-friendly, so I switch the x and the y, but I need to solve for y to be able to see what's happening. So gosh, this one's kind of tricky too, because it's underneath, the y is underneath the radical. So the first thing we're going to have to do is undo that cube root. So what's the opposite of cube rooting something? U cube. So I get x cubed equals 10 plus y. And then it's really easy to solve for y. We just subtract 10. So y equals x cubed minus 10. Or that f inverse notation is x cubed minus 10. Now think about that then. Remember, in the original function, we went 10 in the x direction. So that means on the inverse, we're going to go 10 down, or negative, in the y direction, which, there you go, the minus 10. So that cube minus 10. Let's go ahead and graph that on your graphing calculator. I want you to see the relation. All right, so I have it typed in. Now watch what happens again. Oh, I'm not seeing really the whole graph. But again, just like the last one, I'm going to have to adjust that window a little bit. How about we go down to negative 20 and then I can see a little bit better. There we go. All right, now remember, what symmetry is this supposed to have? The blue with the red, the function with its inverse. Should be y equals x. So I'm going to go ahead and put that in there. Oh, and there we go. We can really see that nice relationship that we would fold right on that line. Take a look at the red graph. Is it a function? Absolutely. It passes the vertical line test. I knew that from the beginning, though, because my original function, the blue one, passed that horizontal line test. Now, one thing that we haven't done for a little bit is to verify that the equations themselves are inverses algebraically. It sure looks like it from the graph, but how do we verify that two functions are inverses of each other? Remember our composition? If f composed with g and g composed with f both undo each other in inverses, that means it should equal the identity function. So we should be able to undo them. So here's what I'm going to have you do. With this original function, I'm going to use the one that says y equals, because it's just a little bit maybe easier to look at. And then this one right here. Well, actually, well, it doesn't matter. We'll just circle these two so you can just see the equations a little bit easier. We're going to see f and g compose. So now they're saying g, well, f with f inverse technically. So f with f inverse, your g is your inverse function, and f inverse with f. So we're going to do the composition both ways and see if we can get the identity function x. So using those two circled equations, we're going to put one into the other and see if we actually get the same thing x for both of them. So we're going to set up those compositions. All right, so let's do f with f inverse first. So we're going to do this half of the equation first. So f with f inverse. So what that means is f of f inverse of x. In other words, we're putting the inverse function into the equation f for the x. So I'm taking the inverse function, the x cubed minus 10, and I'm replacing it in for the x in the original. So we're going to do f of this x cubed minus 10. All right, so let's put x cubed minus 10 in for the x there and see what we get. So that would be the cube root of 10 plus, then I'll substitute in my x cubed minus 10. Well, what happens in that case? Well, the 10s add to 0. You're left with the cube root of x cubed Well, that's just x, so we're halfway there. That's the identity function. Now we're going to take a look at, and we're going to do f inverse of f of x. So we're going to compose them in the other order. What does that mean? I'll do a different color here. So I'm going to do green. So that means I'm going to take f inverse and I'm going to substitute in the function f. So I'm going to go the other way. So I'm going to take this, the function f, and I'm going to replace it in for x in the inverse function. So I'm going to be putting in the cube root of 10 plus x into the function f inverse, which is this guy right here. So that means I'm going to take the cube root of 10 plus x, and it says this rule for the inverse says, hey, take what your input is and cube it, and then subtract 10. Sweet. What happens if you cube a cube root? You get the value underneath. The 10s add to 0, and we're left once again with x. So both of these gave the identity function. So we verified, checked that it's true, that they are inverses of each other. We kind of knew that. We solved it algebraically, but that's how you verify them, that you do the compositions. All right, so let's go back to our essential question. So do we know how to find, how can I find an inverse algebraically? So how do we find an inverse algebraically? You switch the domain and the range. So you switch the x and the y, and then for convenience sake, you solve for y. And again, you can use that horizontal line test to know something about the inverse before you start. The solving for y can be the tricky part, just being able to get that by itself to be able to use it.